Hi class, this is Sir Alex Pasco and welcome to General Physics 2. Today we are going to start our discussion on Lesson 7, which is all about Gauss's Law. It's still related a little bit with our discussion on Lesson 6, which is electric flux. Gauss's Law is basically still electric flux, but this time we are dealing with an enclosed space. So without further ado, let's begin by discussing what would be the goal of today's lesson. So at the end of the day, what I want everyone to be able to do is for you to use Gauss's law to infer electric field due to a uniformly distributed charges on long wires, spheres, and large plates. So what we are going to do is we are going to start our discussion in part 1 in Gauss's law by first discussing what is Gauss's law, how we derive the equation that we use in order for us to solve for the electric field along a uniformly distributed charges and on an enclosed space. And then for part 2, we are going to differentiate how to measure the electric field or the electric flux along long wires, large plates, and spheres. So let's begin by identifying the difference between just the electric flux and Gauss's law. So from our previous discussion in lesson 6, we've learned that electric flux is basically the measure of how much electric field passes or flowing through a certain area. We used this picture before wherein this electric field, this moving line, is flowing or passing through the certain areas like the blue rectangle here, this green triangle here, and this purple or pink rectangle that is inclined at an angle. And we've learned how to measure the electric flux on each of these following surfaces. So electric flux is useful if we want to measure the amount of electric field that passes through a certain area. And we know the equation that we have to use. We use this because we know that the electric flux is actually the dot product between the magnitude of the electric field and the area of the surface, which is also equal to the vector area that is perpendicular to the surface. And the cosine theta, the theta here is the angle between that vector area and the electric field. We know this. But there's actually another equation that we can actually use in solving electric flux. This equation right here is what we call a vector form because we are using electric field and the vector area to solve for electric flux. Another equation that we can actually use to solve for electric flux is called the integral form of the electric flux. And this is the equation. You may notice this is very the same, albeit it's an integral. When we talk about integral, or this sign right here that looks like an S, this is an integral sign. It's actually, or when we talk about integral, we're actually talking about the sum of very, very, very small areas or small samples of that area. So every time you hear me talk about integral, I'm just talking about the sum of very or small particular area. Okay, so this integral form of this equation, or what we're talking about here, it's actually just the sum of the magnitude of the electric field multiplied by what we call the dA, or the differential of the area, cosine theta. So we'll expound this more on later on, and how is this actually useful in applying or in solving for Gauss's law. So in this equation right here, this integral form of electric flux, E is the magnitude of the electric field, dA is what we call the magnitude of the differential of an area, or differential of an area is very infinitesimally small part of the area. Theta is the angle between the E and the dA, and let's now think about how we actually derive this integral form. And then how is this different from this vector form? We are going to answer these question. So let's take a look on how we actually solve for this, or how we actually derive for this equation. What I want you guys first to think about is this surface area right here. Remember, when we talk about electric flux, we are talking about how much electric field is passing or flowing through a certain area. What I want you guys to do then is, yeah, there you go, so that is your electric flux, is to think of these area and cut them into very small pieces. And this pieces is what we are going to call a differential of the area. So for example, you have this whole area right here, and we cut them into small pieces. It may not be to scale, but think of this smaller piece right here. It's a very small, infinitesimally small pieces of the whole area. And what we are going to do is we are going to zoom in on that small piece, and that's what we got right here. So after zooming in, what you would notice is you would have your electric field passing, which is the same on how it passes onto your whole area. And then what you're going to look at is the differential vector area, and you would see that we still have to use it in a way that it is still perpendicular to your differential of area, or that small pieces of area. And then in order for you to find the electric flux, what you have to do is find the angle between these two, this differential of vector area and the magnitude of the electric field. And then what happens is you can actually get the differential of the differential flux. When we say differential flux, it means it's the flux that is passing onto this small piece of area. And we know that in order for us to get this, we just have to use the dot product of the E and the dA. We are using dA because this vector area right here is equal to the area of this small piece. And then the measured flux is just the flux that is passing onto this smaller field. I hope you're understanding where I'm getting at. So now, after measuring the electric flux that is passing onto this small piece, which is a very small part of the whole bigger area, in order for you to find the differential of the flux, we just have to use basically the same equation that we have to use to find the flux, which is E dA cosine theta. So this dot product is basically equal to the magnitude of the electric field multiplied by the area of the differential area cosine the angle between those two vectors. And then in order for you to get the total flux, so let's go back here. So this is the differential flux. This is the flux, or this is the electric flux that is passing onto this small area. Therefore, if you want to find the total flux, or the total electric flux that is passing onto this massive surface right here, not only on this small part, what you want to do is basically add all this small differential flux. So to get the total flux of the whole surface, what you need to do is to do an integral of the differential flux. Remember, when we talk about integral, it's just the sum of all the smaller pieces. So we've measured the smaller flux that is passing onto our smaller area. By measuring all those smaller flux and adding them all together, we can actually get for the total flux. And this is how we actually derive the equation, because we know that the differential of the area is equals to E differential area cosine theta. So having this integral right here, and that's how we got the integral form of the equation for the electric flux. So now let's answer the question, how is this different from the vector equation? How is this different from this equation, which we've been using, EA cosine theta? When can we use this? And when can we use this? Well, the difference is for the vector equation, we can actually only use the vector equation if we have uniform surface and uniform electric field. While this equation right here, the integral form of electric flux, we can actually use this even on non-uniform surfaces, provided the electric field should still be uniform, because if our electric field is not uniform, we cannot measure the electric flux properly. So make sure that the electric field is uniform. So the main difference between these two, between the integral form and the vector form, is that the vector form can only be used if your surface is uniform, meaning it doesn't have a bump, it stays the same shape all over, so you have a square all over. But for the integral form, it is the most general form, which you can actually use to find the electric flux even if your shape is not uniform, meaning it's not flat, it has bumps all over the place. It can be whatever shape it needs to be. So those are the two main differences. Again, why is this very effective? It's because if you cut out a certain surface, whatever surface it is, into very, very small pieces, what happens to those smaller pieces is that they tend to become uniform. And when they are uniform, and you measure that a smaller piece, what you're actually basically measuring is if you measure one of those smaller pieces, is once you successfully measure that, you have successfully measured all the smaller pieces of the big piece. And by combining all those together, you can actually successfully measure the electric flux. I hope you guys are getting what I'm trying to get at. So that is the main difference, and I hope you understand why this is effective. So all of this is still electric flux. So you may be asking now, how is this related to Gauss's law? Now let's go into discussion with that. What is Gauss's law? Well, what is interesting is if you have a 3D surface or an enclosed surface, if you actually measure the total electric flux that is passing onto that enclosed 3D surface or onto that enclosed area, what happens is you would actually have a total electric flux of 0. Why is that? Well, simply because the amount of the electric flux that is going inside your enclosed space is equal to the amount of the electric flux that is exiting that very same enclosed space. And if you notice, if you go back to our sample problems where we used the cube, you would notice that if you add all the electric flux on each of the side of the surfaces, you would notice that the total electric flux is actually 0. And I encourage you guys to go back to our lesson 6, look at sample problem 6.2, and notice that the surfaces, the numbers are basically the same. So the top and the bottom has the same number, left and right has the same number, back and the front has the same values, but the only difference is that one of them is negative and the other is positive. And if you add all those electric flux together, what happens is that the total electric flux is 0. And that is because there is no charge inside your surface. So what happens if you have an enclosed space like this, and an electric field passes by, the amount of the electric field that passes inside or going inside is equal to the amount that is going outside. And what happens? You have a total electric flux of 0. But what happens if you have the charge inside, your source charge, or the charge that is where your electric field is coming from? this is where we use Gauss's law. Gauss's law is useful if the charge where the electric field is coming from is enclosed inside your surface. So what happens is that you have a box right here. For example, this is your box right here. And the charge is inside that box. And remember, for positive charges, the electric flux are radially outward. So you have the electric flux that is basically coming from the inside out of your surface. So what happens is that the amount of the electric field that is basically exiting is now not zero, because you have a charge inside. So when you have a charge inside, whether it be positive, negative, or both, however how many charges you have inside, you can use the Gauss law to measure how much electric flux is passing on that closed surface. So let's differentiate this now. The equations that we have used so far, these equations right here, EA cosine theta, and the equation that we just discussed, the differential or the integral of E dA cosine theta. These are very useful if you have an enclosed surface or a surface, or you have a surface wherein electric flux is passing, or you have an enclosed surface wherein there is no charge inside. But once there is charge inside a closed surface, you cannot use this properly. What you have to use is a Gauss law. So that's where Gauss law is useful. If you want to find the electric flux that is passing into a closed surface, provided there is a charge inside your enclosed surface. And the equation for Gauss law is actually very simple. This is the equation. You have your phi is equals to the total charge inside. Remember, so this is the total charges that is found inside of your enclosed surface divided by epsilon naught. This epsilon naught is what we call the permittivity of free space. So Q total is the total charge inside the closed surface, and epsilon naught is the permittivity of free space, and it is actually equal to 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. So this is the equation that you want to use if you want to solve for the electric flux of enclosed surfaces with the charge inside, meaning the electric flux is not coming from the outside, but it's coming from the inside. That is where Gauss's law is. So now let's understand that this is the equation. Phi is equals to Q total divided by epsilon naught, or the Q total divided by the permittivity of free space. So the permittivity of free space value does not change. I just want you guys to remember that this is just equal to, or always equal to, 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. Similar with K, these values are constant. K is always to 9 times 10 raised to 9 Newton meter squared per coulomb squared. But for the permittivity of free space, it's 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. So before we continue on with more understanding of Gauss's law, just a little bit of information about Gauss's law. The one that formulated this equation is a German scientist by the name of Carl Friedrich Gauss. And thing that I want you guys to remember is that Gauss's law is the total flux through a surface. Most importantly, that I want you guys to remember, it should be an enclosed surface, and it is the total flux is actually total to the electric charges inside divided by epsilon naught, and that's where the equation comes from. So meaning the electric flux of an enclosed surface with a charge inside is directly proportional to the amount of the total charge. So Q is directly proportional to the Q total, or the total number of the charges, and is also inversely proportional with the permittivity of free space. Okay, so there's things that I want you guys to remember. So another thing that I need you guys to remember is the total flux can either be positive or negative depending on the sign of the charge that is found inside. Positive charges has an electric field that are always radially outward, which means if I'm going to draw that, if I have let's say a sphere, and inside the sphere I have a positive charge, I know that the electric flux should be going outside of that sphere. And interestingly, since it is radially outward, it has the same direction with the normal. Remember what normal is? This is your area vector. So it has the same direction. So if I'm going to look at, this is my sphere, this is my electric flux coming from the positive charge, and my area vector has the same direction with the electric flux, which tells me that the flux, or that the electric flux, is positive because they are in the same direction. But if I have a sphere with a negative charge inside, I know that my electric field is directly outward, or directly inward, because the direction of electric field for a negatively charged particle is always radially inward. So what happens is, if I have a negative charge, the electric flux is going this way, but the normal force is going this way, and they are in the opposite direction. Therefore, the electric flux is negative. So this is something that I want you guys to remember. Okay, so the total flux can either be positive or negative depending on the direction of the normal and the direction of the electric field. So if you have an electric field that is going the same direction as your normal vector, then the electric flux is positive. But if you have a negative charge, and the electric field for negative charge is directly inward, but your normal is directly outward, therefore your electric flux will always going to be negative. One way to remember this quickly is positive charge, you would have positive electric flux. Negative charge, you'll end up having negative charge. And again, this is only true for enclosed surface, okay? Because for Gauss's law, we only use this for enclosed surface. Now let's discuss how we actually derive the equation for Gauss's law. How we derive the equation phi is equals to Q total divided by epsilon naught. How we derive on this equation? Well, I want you guys to think about this scenario. We have a sphere with a radius r, and inside the sphere we have a positive charge. Remember, for positive charge, the direction of the electric field is radially outward. So we have our electric field in our purple arrows right there. And what happens is similarly what we did with the electric flux earlier, where we took the differential of the area, or we basically cut them into smaller pieces. What I want you guys to do now is to focus on a very small pieces, or very small piece of that surface of your sphere. And what we are going to do is we're going to look at this very small, infinitesimally small piece of that surface. After zooming in, what you would notice is you would have your electric field passing onto that small piece of that surface. And similarly, remember, for enclosed surface, our vector area is always directed outward. And if we actually look at the very small part of that surface for a sphere, what you would notice is you would have the differential vector area at the same direction as your E. Now we can actually now find the differential of the electric flux. As usual, the differential of the electric flux is basically the dot product between the magnitude of your electric field and the area vector, which in this case, this area vector n is equals to the dA, or the surface of that smaller differential area. And same thing happens. In order for you to find your EDA, you just have to find the angle between the dA, or the normal vector, and the electric magnitude of the electric flux, which is cosine theta. So the differential of the flux, again, the differential of flux is the flux that is happening on just this small surface, is equals to EDA cosine theta. And interestingly, since you have no angle between these two, because this is an enclosed surface, so the direction of the electric field will always be parallel to the direction of your normal vector, which in this case you have your differential, which is equal to the differential of the area. So cosine or theta will always going to be 0 degree. So what's left is the differential of the area is just equal to E differential multiplied by the differential of the area, because cosine 0 degrees is equals to 1. So EDA multiplied by 1 is just EDA. Now what we're going to do is we are going to take this and we are going to turn it into this equation. So how are we going to do that? So understand that the total flux again is equals to the integral of the differential area. So if I want to find the total flux for my enclosed surface, I just need to find the integral of my differential flux. And remember, the differential flux for my example now is just equals to EdA. So what we're going to do is we're going to take this differential of the electric flux multiplied by the differential of the area. The electric flux is always constant. It doesn't change in value. Therefore, we can just actually pull it out of the integral. So I hope you guys remember. I'm not sure if you've taken calculus. I think you've taken calculus. You do this in calculus, doing differential of an area or doing integrals in calculus. If you have a constant value for an integral, you just have to pull out that constant value and do the integral of what's left on your equation. And then after doing that, what we are going to do is understand that the integral of the differential of an area is just the sum of the smaller pieces. Since this dA, the sum of all the smaller pieces, is actually just the whole area. Meaning, again, differential area is the very small part of that surface. So by adding them all together, that small surface, and you add all those smaller surfaces together, what you will get is the total surface. So phi, or the electric flux, is just equals to EA. So again, this integral of dA is just the sum of all the smaller areas, and the sum of all the smaller area is equals to your total area. In this case, it is a sphere. And then what I want you guys to remember now is we've discussed about electric field, and we know that the equation for electric field is equals to K multiplied by Q divided by D squared. But since we are talking about the sphere, we are going to change our D into radius, and the radius, we're going to use R to denote radius. And another thing that I want you guys to think to know is, or just to note here, K is, we've discussed this as the Coulomb's constant, and Coulomb's constant is actually equal to 1 over 4 pi epsilon naught. We are not going to discuss the shenanigans how we derive this, but just know that the Coulomb's constant is equals to 1 over 4 pi epsilon naught. So what we're going to do is we are going to substitute these values to our equation right here. So we get the phi is equals to, our E is equals to K Q R squared A, and it is actually equal to, we're going to change the K to 1 over 4 pi epsilon naught multiplied by Q R squared A. Right? And then what's left is we're just going to mix this together. We'll get Q 4 pi epsilon naught R squared multiplied by the area. Next, what I want you to know is we are dealing with a sphere here, and the area of a sphere is equal to 4 pi r squared. This is an area of a sphere. Then we are going to substitute the value of our A onto our phi equation. So phi is equals to Q multiplied by 4 pi epsilon naught r squared multiplied by the area of a sphere, which is 4 pi r squared. And what you notice is we can actually cancel the 4 pi and the r squared. 4 pi r squared. And what's left is Q epsilon naught. And that's how we derive the equation for Gauss's law. Okay, so in the end, I just did this so you understand how we got from how we got the equation for Gauss law. So now that we understand Gauss's law, there are several things that I want you guys to remember. So again, this is the equation for Gauss law. First thing that I want you guys to remember, the total flux for a closed surface does not depend on the size of your area. Meaning, if I have this sphere right here, you can see it's a square, but think of this as a sphere, and it has a radius r. And what I want to do is I'm going to increase my radius twice. So I'm going to increase the size of my radius by 2 times. What happens is that, so this sphere has a positive charge inside, and we know that this sphere would have an electric field going outward. But first, let's talk about the radius. What I want to do is I want to increase the radius twice the size. And what happens if I increase the radius is that automatically my sphere would get bigger. So the new size of this sphere is this red circle right here. So that's the new size. So it has a magnitude of 2r. And the electric field of the positive charge inside is still radially outwards. What I want you guys to understand and remember is that the total flux does not change. The total flux that is happening on this smaller piece right here is equal to the total flux that is happening even if my sphere is bigger. The reason for that is if you look at your equation, and which we derive from this is the last equation that we derived before we canceled all the 4 pi r squared. We just did that. As you would notice that using the inverse square law, we actually canceled the area. So this is the area of a sphere, remember? And by canceling the area of the sphere, what happens is that the size of the sphere does not matter. No matter what the size of the sphere is, the electric flux remains the same because of the inverse square law. So by from the equation, you notice that we just cancel the area all over. So meaning the area of your enclosed surface does not affect your electric flux. Okay, so even if I have this sphere right here, and then I increase the surface right here. As long as my charge is not changing, my electric flux remains the same. Number 2, even if the surface is not even, the flux remains the same. Remember, since we use the integral to solve for our equation, the integral form of the electric flux is very helpful when we want to find something that is uniform. So even if my surface is not even, so even if I have a sphere or a cube, so these are very even. So if I have, for example, like a pear shape, so something like that. So if I have a pear shape and I have a positive or negative charge inside, and I want to find the electric flux for this pear shape, I still can use Gauss law, because even if the surface is not even, the flux remains the same. So this is very useful in looking for electric flux of even on surfaces that are not uniform. Number 3, even if the charge is not centered, the flux remains the same. So even if my charge is not totally centered, maybe it's near the bottom air outside or the bottom part of your enclosed surface, or on the left, whatever, no matter where the charge is, as long as it is inside your enclosed surface, the flux remains the same. And the only thing that you have to notice, or you have to note, is that your enclosed surface must be closed. There shouldn't be any holes on your surface. Otherwise, the flux will change. Having a hole on any of your surfaces, the Gauss law breaks apart. It does not work anymore. So it has to be closed. Lastly, the flux also changes if there are more than one charge inside the closed surface. So we've been only talking about a charge that is inside, but there's only one charge. But what if we added another charge? Or I have another charge, or let's say we have 4 charge. What happens to the flux? This is also the only time that the flux changes. So for example, we have 2 charges right here and they're off-centered. So if I only have one, the electric flux remains the same even if this charge is centered. But if I have 2, then the flux changes. And so how are we going to measure the flux for a situation where we have more than one charge now? Well, it's simple. You just have to add all the charges inside divided by epsilon naught, or the permittivity of free space, and you can get your new electric flux. So just remember that the total flux is is directly proportional to your Q inside, or in this situation, if you have more than one, the total charge Q inside. So let's try this sample problem. Calculate the total electric flux for each of the closed surface A, B, C, and D as shown. Note that Q1 is equals to positive 3 columns, Q2 is equals to positive 1 columns, Q3 is equals to negative 5 columns, and Q4 is equals to negative 4C, or negative 9 columns. So how are we going to solve this? So we are given the values. I'm not going to write the given anymore. They're written here. So I'm just going to write what is being asked of us. What it's asking is the electric flux for surfaces A, B, C, and D. And the formula that we have to use is, in order to find the electric flux for an enclosed surface with charge inside, we just have to have the phi is equals to Q total divided by permittivity of free space. So let's write our solution. Let's begin with A. So the electric, or the total electric flux for A, if we look at our surface A is this. So In order for us to find the electric flux for an enclosed surface, what we just want to do is find the Q total of the charges. So all the charges inside, all the charges are actually just inside of A. So Q1, Q2, Q3, and Q4 are all found inside A, or surface A. So the Q total is equals to A is equals to positive 3 columns plus we have your B, which is positive 1 columns, and then we have our Q3, which is plus negative 5 columns, and then you have plus negative 9 columns. So, and then permittivity of free space is equals to 8.854 2 times 10 raised to negative 12 coulomb squared per Newton meter squared. So 3 plus 1 is equals to 4, minus 5 is equals to negative 1, minus 9 is equals to negative 10. So that's just basically negative 10 columns divided by 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. So what's left is that the electric flux is actually equal to negative 1.1294 times 10 raised to 12 Newton meter squared per coulomb. So this is the electric flux for my surface A. And we just have to do that everything for B. So for the electric flux for B is equals to, what are the charges found inside B? It's only Q2. So Q2 is equals to positive 1 coulomb. So this positive 1 coulomb multiplied by 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared, and that is equal to equal to 1.1294 times 10 raised to 11 Newton meter squared per coulomb. Now let's try to find C, the electric flux for C. As for C, what is found is Q1 and Q2. So you just have to add everything, Q1 and Q2. So or you just have to add Q1 and Q2. So that's positive 3 columns plus positive 1 columns. That is equals to 4 columns divided by 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. So our the electric flux for our surface C is equals to 4.5176 times 10 raised to 11 Newton meter squared per coulomb. And lastly, for D, the electric flux for D, if you look at D, this is your surface D, and everything is inside. Therefore, it is the same with A. So that is just positive 3 columns plus positive 1 columns plus negative 5 columns plus negative 9 columns divided by 8.8542 times 10 raised to negative 12 coulomb squared per Newton meter squared. So the electric flux for D is just equals to the same value as A because they all contain the charges. Negative 1.1294 times 10 raised to 12 Newton meter squared per coulomb. So that's how you find the electric flux. Quite easy, right? So that is all about the first part of electric flux. The second discussion will revolve around how to find the electric flux along a long wires, spheres, and or specifically large plates. Okay, so if you guys have any question about Gauss's law, it's just again remember Gauss's law is measuring electric flux still, but this time we are measuring electric flux wherein the electric flux is outside your enclosed or inside your enclosed surface. Thank you so much, and may you guys have a great day.